Osmosis. So you've learned osmosis before. You probably started learning it in 7th grade. There are a lot of ways that people memorize osmosis, but in phys, memorization usually fails you when you need it. So what I want to do is teach it to you in a way that hopefully you'll understand it instead of memorize it. So really, the important thing about osmosis is that it's a special instance of diffusion. It's diffusion that meets 2 criteria, and this is important. It's diffusion of water, yes, only water, across a selectively permeable membrane. What it looks like water is doing is it looks like water is moving toward a higher solute concentration, but that's not diffusion. If water is diffusing, then water should be moving from water's high concentration to water's low concentration, which is what it's doing, okay? And the membrane, importantly, has to be selectively permeable. And what do I mean? I mean this. I mean that the membrane that you are seeing right here, the membrane that you're seeing right here is permeable to water, because most membranes are permeable to water, and not permeable to this solute. I don't know what that solute is. Let's make it glucose, because glucose is not easily transported straight across the cell membrane because it's water soluble and it's large. So if the membrane were permeable to the solute, then the solute would move and it would be simple diffusion. But in this instance, you've met both of these criteria. You are going to have a selectively permeable membrane, and you're going to have water can move across it and the solute cannot move across it. So this is super important. So this is passive transport, right? Diffusion's passive transport and osmosis is passive transport. It's just diffusion, but it's a special criteria, a special instance of diffusion. And it depends upon the concentration gradient for water. But of course, how rare is it that you're actually given water concentrations when anything else is in there? So in this particular figure from your textbook, they gave you water concentrations, and that's all lovely. But generally speaking, they're not going to. They're going to give you the solute concentration, and they assume that you will know that whatever is not solute is water. So let's just flip around and think about this for a second. Pretend you're not given this water concentration at all. And this says that inside the cell you have a 0.3 molar or 300 milliosmol solution. Now, it's not real chemistry. You don't even have to know what a milliosmol is, because you can compare 0.3 to 0, right? And know which one's higher, right? So in this particular instance, what they will give you is, oh, there's a higher solute concentration in here and a lower solute concentration out there. And the first thing you will want to do is to try to diffuse the solute out. But this is what we call a non-penetrating or impermeable solute, meaning generally, because of the chemical characteristics of the solute, it is not going to go across that cell membrane. So if the solute can't go, then the water will go. Okay, so the solute ain't going anywhere. So what's going to happen is, even though you're given the solute concentration, you have to flip your brain around and think about the water concentration. So what's going to happen is, if the solute is lower here, that means the water is higher, right? The solute is higher here, that means the water is lower, because this is just solute and water solution. So I'm going to move from a high water concentration to a low water concentration, okay? Again, people constantly tell you, and it's even in this little animation that I linked, that water moves toward the high solute concentration. Water doesn't care about the solute concentration. Water moves down water's concentration gradient. So, but here's a cute little animation, except that I don't like the reason they told you. It's just this little cutie guy. So you can see water moving in, water just moving in and out, and water moving out. So we're about to talk about these 3 situations. And I know you've done it before, but I need you to understand it, because moving water around in the body is a big deal. And most of the time it moves because of osmosis. And so you are going to need to be able to predict which direction water is going to move, even when you're often only given the solute concentration. So your ping that should occur in your head that shall tell you that osmosis instead of diffusion is going to occur, is an impermeable or non-penetrating solute. Okay, so now let's look at the types of solutions, and we'll sort of draw them out. And I know you've drawn something like this before. Okay, so I've got three solutions right here, A, B, and C, and what I'm going to do is I'm going to try to put, I'm a good scientist, so I'm going to hold everything consistent but one variable. And I'm going to put 3 different red blood cells. Okay, they're supposed to be identical. Just stick with me here. And you should know, if you don't, let's just remind you that cells are not empty. Cells have solutes dissolved in them. Okay, so I'm going to try to represent this really simply by saying, okay, these cells are all going to have some of the solute X. And importantly, this is a non-penetrating solute. Okay, so let's just say they all have the same concentration of X in them. Most cells are pretty similar, especially when they're the same type of cell. So I am going to vary what varies more frequently. The intracellular fluid of similar cells does not vary very much, but the extracellular fluid certainly can. You can have changes in pH. Remember, you can have, that's where you get exposed to pathogens or toxins first. That's where your nutrients would come first, all of that kind of stuff. So the extracellular fluid, which is represented in the outside of this beaker here, the extracellular fluid definitely does vary. I'm going to vary these in 3 different ways, and then I'm going to try to figure out what water is going to do. So I'm going to say, okay, this first one, A, what I'm going to do is put this cell in pure water, meaning it will have no solutes in it at all. Okay. Cell B, what I'm going to try to do is balance out the concentration inside with the concentration outside. Good. And I know that's not concentration exactly, but just go with me. Assume that they had similar volumes, which of course they don't. And then in situation C, solution C, what I'm going to do is put it in a relatively concentrated solute solution. And again, this is a non-penetrating solute. Let's say it's glucose. Okay. And what I need to do is I need to figure out 3 different times the answer to this question. I need to figure out where water is going to move and how it's going to impact the size of the cell. Okay, so same question 3 different times. In situation A, where is water going to move? Okay, now again, the first thing you want to do is move the solute, but it's a non-penetrating solute. So now I have to figure out the water concentration. Where is water higher? Intracellular fluid or extracellular fluid? Well, water's higher in the extracellular fluid because the intracellular fluid has some solute in it. So it's going to be higher in the extracellular fluid, and water is going to move from its high concentration to its low concentration. Water is going to move in. What's that going to do to the size of the cell? Well, the cell will get larger, okay, may become a sphere even if it's a red blood cell. And if it gets big enough, it can cause lysis, which is called hemolysis in red blood cells. Okay, so a bigger cell. Okay, in situation B, same question. Where is water going to move, and how is that going to impact the size of the cell? So, in this situation, you're tempted to say that water isn't going to move anywhere. But I set up the experiment so that the cell membrane is permeable to water, and so you can't just make it impermeable. So really what's going to happen is water is going to move both in and out, but no real net movement of water. So the impact is that the cell over time is going to be about the same size, supposed to be about the same size. Okay, and then C, same questions. Where is water going to move? And what is the impact on the size of that cell? Okay, so don't move the solute, can't move it, break the rules. Try to figure out water concentration. Where is water concentration higher? The inside of the cell has fewer solutes and therefore more water, and the outside of the cell has more solutes and therefore less water. So water is going to move outside the cell. what is that going to do to the size of the cell? It's going to shrink it. And you guys probably remember that shrunken little cells. That's called crenation. Okay, now all we need to do with this picture is now label the solutions. Okay, and you're labeling the solutions with reference to the cell. So each solution, did it have more solute, less solute, or the same solute as the cell? Okay, so we're going to use some prefixes that you've heard before. Iso meaning same, hypo meaning below, hyper meaning above or more than. Okay, so one of these situations, A, B, or C, had the same amount of solute as the cell. Which one is it? Of course, yeah, it's B, right? So this is an isotonic solution. And we are not labeling the cell, we're labeling the solution. The cells were all the same. Okay, one of these solutions had way more solute than the cell. A, B, or C. Way more solute than the cell. It is C, which is a hypertonic solution. Okay, and of course this will make this question really easy. One of these solutions had less solute than the cell, and that is a hypotonic solution. Okay, so I've remembered this since I learned it in 7th grade, because if you're hyper, do you get skinny or fat? Skinny. And in 7th grade, hippo, big fat cell made sense to me, and then I didn't need a third one because that was the only one left. May not be the most clever memory tool ever, but it certainly worked. Okay, so the types of solutions. Let's talk about them with reference to the human body. An isotonic solution, same tension, the same amount of solute as the cell. An isotonic solution has no net change in cell size. It still does have water movement in and out, but it has no net change in cell size. This is, for instance, when you become dehydrated or you have to give somebody a saline solution, you would like to give them a saline solution into their bloodstream that did not change the size of their blood cells, right? You don't want them to lyse, you don't want them to crenate, so you're going to give them an isotonic saline solution, which in most instances is 0.9% saline, and no net change in cell size. Good. Hypertonic, hyper means above. The solute concentration outside is less than the solute concentration inside. This is why you don't want to drink salt water when you are stranded on a desert island, because if you drink salt water, what happens is, as the salt water goes by your mucous membranes and comes into contact with all of those epithelial cells, the cells are exposed to a hypertonic solution, and it sucks the fluid out of the cells as it goes by. And as it does that, you end up losing more of your body water. So although you may think you're quenching your thirst, you're ending up dehydrating yourself. It's also the reason why when you spend a lot of time in salt water, your skin can get really dried out. Okay, and then the hypotonic solution, hypo means below, and the solute concentration outside is less than the solute concentration inside. This is why you don't shoot yourself up with pure water when you are dehydrated. So when you're dehydrated, if you shoot yourself up with pure water, first of all, your kidneys would try really hard to compensate, but let's say that didn't work. Shoot yourself up with pure water, what can happen is you can overwhelm your kidneys' capacity to regulate your water concentration. You can actually cause your cells to increase in size and change function, and eventually you could cause hemolysis. So that is the effect of a hypotonic solution. There is a good little 5-minute animation video of osmosis that I've linked for you here if you guys need to look at it a little more closely. And that's it for osmosis.